under jet lag. And I think I'm too. So just in case that I'm not able to speak the point, every point I want to make, I think I really rely on people asking me questions so that I can make up for things I really forget. So, so there is a slight change in the title of this talk. And instead of just focusing on assistive learning, so I'm thinking, okay, maybe the good idea is to give people a broader picture and try to emphasize on a couple of things. One thing is we're looking at one type of a multi-agent system, which is looking at the coordination, but it's a guided coordination, but also looking at the not just a game theoretic paradigm, but asking yourself. I think actually the topic of this workshop is a dynamic games, multi-agent dynamic games. So I think it's very important for me to elaborate what is multi-agent. And also, what is dynamic and what is games and why they are important in this context, right? So and also how the learning is going to come into place. And all these questions are something that we have been talking about for the entire day. So starting from the multi-agent systems. So I think this is something that people have already mentioned and throughout this entire workshop, starting from smart manufacturing where robots have to work together to complete a task, and also human robotic collaboration. I think there is a talk later on after mine, and it was going to be professionally on this topic. And also there's a swarm and there is a transportation system and so on and so forth. So what is important is that, well, all these agents has to work together. Well, it doesn't have to be work together, but sometimes there could be malicious agents actually can manipulate the team and also manipulate the other agents. But also, let's say, suppose here in this context, we are looking at how the agents actually can work together and their teaming process. Of course, I mean that there is a agent matching and how we can choose the agents to work together, and also the moment we pick these agents and how they can coordinate, and also at the very beginning in this morning, and there is a lot of emphasis on the communication. And the goal of the coordination is really try to hopefully A and B and work together, and 1 + 1 is greater than 2. So, and when it comes to coordination, so we need a heterogeneous agents work together because they have different capabilities in terms of actions and computational resources, as well as their roles. So for example, some agents has more resources and they can act as leader, and some agents may not have that level of intelligence and has to work as a follower. So, and now the question is how this is a teaming process can be done, not a top-down process. In other words, okay, I'm going to be a person designing the entire process from very top-down, telling you to do A and you to do B, but instead, hopefully there is a bottom-up process that allows us to create a strategic teaming and coordination, and so that, well, the agents level and the object levels are going to be satisfied. So, I mean, just giving people an example here. So what we are looking at here is a class of strategic coordination, what we call the guided coordination. In other words, so one type of agent, the superior agent, is going to guide a less sophisticated agent so that the heterogeneous capabilities can be leveraged to complete a task. So there are other type of strategic interactions, for example, the distributed interactions, where, like, say, there's a team of identical agents try to work together, thinking about, like, say, there is a swarm and every agent is working, every agent has a similar capabilities, and they are having identical informations and response patterns, and they're going to work together to achieve a objective. Or there could be also a system coordination where you can have a teams within teams and the system level interactions in order to achieve a bigger objective. Thinking about a lot of critical infrastructures are like that type. So now the question is, why we want to look at games, and especially game theoretical models or dynamic games? Well, the first way I think is that, well, think about the games models is actually a way, it's a description of what the situation, or it's a physics. Of course, we don't have physics here, but thinking about we want to have a physics-like description model for the strategic coordination. So then we have to do is to describe the agent's capabilities. For example, the capabilities of agents could be described through their utility functions, objectives, and reasoning process, and so on and so forth. For example, I mean, the reasoning process, their rationality, or sometimes boundary rationality, they can also be captured through the patterns of interaction. At the same time, the autonomous decision-making, it results in a equilibrium seeking. And I think there's an earlier conversation or earlier talk, which is talking about a generalized Nash equilibrium. And this equilibrium seeking process is going to be one type of autonomous decision process that we could prescribe the agents to do or describe the agents to do. And also the performance coordination mechanism, end of the day, we need a metric. And that metric could be measured through the equilibrium or non-equilibrium solutions. And that's possibly the reason why we are so much interested in the Nash equilibrium solutions. But sometimes, well, we may not be using Nash equilibrium because the equilibrium may not even exist, especially we're dealing with a non-stationary environment. So, and also later on, the good thing about having this type of description is like the reason why we want to have physics is that we want to change the physics. So, and the good thing that we have the game theoretic models or these game descriptions is that hopefully we can design the mechanisms and telling people how to play these games. And eventually different games is going to describe different types of interactions. And for example, a Nash games maybe is a good idea to describe distributed coordination, and a Stackelberg games maybe for guided coordination, and the games and of games possibly would be a good idea to describe a system of system level interaction. Just to give you an example, for example, like say suppose, I mean, I think this is probably a game theory 101. In a context, let's say suppose on the left-hand side, we have two players, right? So one player is choosing up and down. The green player is choosing a right and left. So these agents are not really communicating. These agents are making decisions on their own. So in other words, in terms of the communication structure is that everybody is looking at their local information and making decisions on their own. So in other words, when you go to the information structure setting, so every agent is looking their own, having their own limited observations, and they're not communicating with each other. And this is the reason why we often land with the Prince dilemma, which results in inefficiency of the Nash equilibrium solutions. So this is when we have when there is a lack of communication, and when every agent is acting selfishly or according to their interest and best respond to the others in order to act in their own benefit. On the other end, we also can have the Stackelberg type of game. And this is a type of, we can have two viewpoints. One viewpoint is in terms of the looking at structure-wise, right? You want to look at, okay, there's a leader sitting somewhere, and leader is going to take an action first, and then the follower is going to look at what leader does, and then and respond to what leader is going to do. So this is a type of the leader-follower behavior. So you can view that as a leader has a higher reasoning capabilities, and he can actually anticipate what the follower is going to do, and so they can take their action first, and then the follower is going to follow accordingly. Also, we can also interpret this from an information viewpoint. So leader is going to provide information and plan the information, and the follower is going to observe the information. In other words, and this structure naturally is able to give out action as or signal actions as a information structure. So this is a different type of games eventually lead to different type of interactions. Now, when it comes to this workshop, theme of this workshop, we'll look at the dynamic games and for multi-agent systems. And one important aspect is what is the information structure that we are seeking. In other words, like who has the information, who observed what, and what's their interaction patterns. And based on that, you will actually going to pick the right description of the game in order to capture these type of interactions. And one of the example which I like was, I think this is a classical dynamic game problem, is what we call the lady in the lake. So a lady in the lake problem is apparently by the name, there's a lady in the lake, and there is a lion, and there is a man in this case, is going to, lady is in the lake. So, and this is the thing about the sea in the center of this lake, and this is where the lady is. And then there is a man or the lion, and he cannot swim. A lady can swim. So the man can only intersect the lady when she reached the shore or the edge of the lake. And the lion or the man can walk around or run around the circle at edge of the lake, so that by hopefully the person or the lion is going to capture the lady, for example. This is the very classical example, and this is apparently is a dynamic game. So the lady has to figure out where to swim and how to swim, how to where to seek to escape, right? And the lion, of course, is trying to figure out, okay, what is the trajectory? And so that he's going to A or going to B. So this is apparently a dynamic game with the multiple stage of actions. And hopefully, well, we want to find a right structure of the game to describe this entire context. So, well, so what is the dynamic game structure? I mean, I think the first element is what is the state. So the state, let's say N is the state here, or here is what I call the nature, but the nature is going to realize a state. And then there's a player one is going to do something, and player two is going to do something else. And eventually the player one and the player two, they have information structure, which is going to be prescribed based on what they can see. For example, in this case, the player one is not able to, the player one does not know what the nature does, what the state is, but the player two does. So in other words, in this context, so the player one and player two have different information structure, or the player one or player two may have the same information structure, and so on and so forth, that they actually can follow through this entire game process. In other words, the state is going to influence the players one and player two's action, and then eventually the players one and players two's action is going to help the state to evolve. So knowing that, so going back to this process, so of course this is a lady in the late game. So in the state is possibly you can choose is the position or the where the lion and where the lady is. And it just make the problem simpler. Suppose I have only A and a B. So instead of like the lady going to going around like say all possible places along the lake, but only she can go to either A or B. So then this is one of the interesting studies here is that while this entire process of the game, I think there's many strategies actually can prescribe as the outcome of the analysis of the game. For example, if the lady is going to, like say, if the lion does not really know where the lady is going to go, could it go to A or B, the left or right? Right. So, and then the lady, maybe the best thing for the lady to do is going to the middle. So I try to confuse what is the lion or the man, where I'm going. And the man does not really know where the lady is going. And then he is going to wait and until figure out, okay, actually going to the right. So I'm going to capture you at the right. Or the person, the lion could be very strategic and just follow exactly where the trajectory of the lady and then eventually go to the right, or and the lady is going to be a little bit going to be zigzagging and eventually try to go to very in the end is going to the right. So there's a lot of possible strategies that actually we can use analysis to figure out how the lady is going to escape. Again, this is a classical problem. So when it comes to a guided coordination, so the guided coordination is the same story, but the difference is that now that you have a two-player games, when you have a leader who guides the followers to do something. Now the question is that, well, the leader is going to have more capabilities in terms of the computational resources and actions, and the follower is going to have is going to look at what the leader has done, and so that make a decision and a response, and so that the entire task is going to be accomplished. So an example that we pick was this is a multi-robot object rearrangement planning problem. So in assembly line. So for example, let's say in a smart warehouse, you have two robots and there are both robotic arms and they want to rearrange some products in an orderly way. So, and there is a leader, one of them is leader, and the leader can anticipate what the follower is going to do. So in other words, the leader is, the goal is the same for both agents. So the leader is going to sense a recommended action to the follower, and the robot is going to act myopically and in a less feasible action. So in other words, there's either you follow or not follow, or pick your own, right? So then this entire problem becomes a stochastic Stackelberg game, because you do not know whether the follower actually is going to follow the recommendation or not. So, and eventually this problem can be formulated into a leader follower type of a bi-level optimization problem, where the leader is going to achieve an objective subject to what the follower's possible action is going to be. So in other words, in order for maybe a good example is this, in order for an advisor, a PhD student advisor, right, to give PhD student the right advice. So I need to know what is the PhD student is going to do in response to my advice. Is he going to follow or not? If I know that he is not, I know, let's say his objective is to find a job, then I need to give him the right thing to do so that he is going to follow my advice, right? Otherwise he thinks, oh, okay, there must be something about my advice or want to really work. A student have all the reasons not to really work, right? So maybe that's true, maybe that's not true. So thinking about then as an advisor, if I want to be strategic, then I have to know what is the goal of the student so that you can guide the student better, so that you can achieve the win-win situation together. So the same thing in this context. So suppose the leader wants the follower to achieve a goal. So, and then the leader has to reason what followers is going to do if I'm going to tell the follower to do something. So that signal that he is going to send to the follower. So this entire process can also be done through a receding horizon planning. In other words, while I may not be able to know what is the plan entire 5 years of what a PhD student is going to do. I cannot give all the advice ahead of time, right? So I have to adapt my advice over time so that I adjust what my advice is based on what a student's response is. So similar in this context too. So knowing like whether the robot actually, the follower robot is actually deviating away from my recommendation or not, or my anticipated action or not. So I'm going to do the planning in a receding horizon so that I can adjust to the online observation of the follower. So this is so far so good, and this is all based on a model-driven context, and where you can use online computation to create a resilient planning. So in other words, maybe the objective of the student, the objective of the robot changes over time, or there is a disruption happens at some certain point, so that you want to make the entire planning more resilient over time. So, and there are some experimental results which try to show that, okay, you can use the greedy mechanisms, you can use other type of mechanisms. Eventually, the guided mechanism, knowing what the followers' incentives are, eventually is going to help you to outperform other type of methods. So, knowing that this is a promising coordination process, well, of course, there's a lot of other challenges in the process. For example, well, I may not even know what the objective of my follower, and I do not, in this context, may not even know the dynamics of my follower, right? So now the question is, how can I deal with this incompleteness of information? Well, and this incomplete information, oftentimes in a theoretical model, we oftentimes have to deal with estimation. We oftentimes have to deal with a Bayesian process. We have to deal with games with the partial information, or in a lot of, in a more sophisticated way, you can also sometimes in the context you absolutely have no idea what is your unknown unknowns. You sometimes also have to conjecture what your follower is going to do, and then eventually lead to a consistent conjecture that actually consists with your observations. But in this context, well, we can actually do something else. So what the second study that we do is looking at, suppose that we have this multi-robot trajectory guidance problem. So in other words, I want to, let's say, suppose I am a robot A, I'm a UAV, and I want to guide a UGV to reach a goal, so that the UGV is going to avoid the collision, for example. Then, of course, I may not know who is the UGV I'm working with. So what I need to know is that, well, maybe I need to really understand what is the dynamics of the UGV that I'm guiding, so that I actually can guide it better. So an example here is that this eventually can be also a model in a similar way as we have seen earlier. So you can think about the leader is going to make a planning from 0 to t-1, and its planning outcome is going to depend on what a leader's action is and what is the follower's action is, so that they are, if the utility or the cost is going to be determined by the actions of the follower and actions of the leader. The follower is going to respond looking at what is here, this problem. The follower is going to solve the following problem. The following is going to look at what his leader's action is, and so that he is going to figure out what is right thing to do. So, and this is of course so far so good. But the question is, when it comes to leader's problem, it is really hard for me to know whether, what exactly the problem that follower is actually solving. So instead, what I really need to know in an equivalent way is I just want to know how leaders actually respond to me. So instead, try to figure out, okay, this is the optimization problem that my follower is solving. Why don't we just use a dynamic process to try to describe how the leader, the follower is actually responding to me, right? So instead, because I do not have to know what is my student's intention is. I just have to know what he does, what his moving process is. So in order for us to know the moving process, well, we can use Kuhlmann operators based on observations to figure out what is the dynamic, and using an approximation to create a dynamic process where we can lift the entire nonlinear operator into a linear operator, so that we actually can create a state in the observational space that is going to be in linear as an approximation in the state of observations and also in a control U. So this linear approximation enabled by Kuhlmann operator allowed us to actually try to learn what the dynamical system of the follower is. So knowing that, we actually can create a better guidance for the follower to go from the source to destination, and at the same time avoiding the obstacles. And you can always create a baseline framework, which is totally based on the optimal control approach, which is based on the model that you have already known ahead of time. And this is the baseline. And you can see that the approach with the Kuhlmann operator actually can helpfully, can successfully guide the follower out of this maze, or guide the follower to achieve the objective or the destination. But other approaches, like thinking about just a neural network approach or our dynamic mode decomposition type approach, may not be sufficient when you just learn the dynamics, but not able to guide the performance when there's obstacles sitting here. So this is a one learning approach, which we are talking about the Kuhlmann operator try to describe the physics of the follower or dynamics of the follower. But there's also a lot of cases where the learning becomes more complicated, because when it comes to human, so we don't have physics. So in other words, whether the human is following a Newton's law or physical law, it's really hard to conceive. So instead, while we also need to find other ways, hopefully we can learn, so that when it comes to interactions between a machine and a human, well, we also need to create a model that allows to capture humans' limited cognitive capacity. For example, the human can make mistakes, human may not be rational, and human may not have the physics model as we can describe as what we have seen earlier. So, and this is an example that we try to use. So, and a good example to illustrate this is the assisted driving. So, for example, like say, suppose we have a assisted driving system, and the goal is to guide different type of users, different type of drivers. But unfortunately, I do not know what type of drivers I'm dealing with. The drivers could be very aggressive. The drivers could be very cautious. There are different types of driver I'm dealing with. So, and the way for us to learn what to serve the driver better is to create a meta-learning process. So the meta-learning process starts with, okay, let's say suppose I do not know the specific driver that I'm dealing with. So, but I can have a nominal behaviors of a set of drivers, which I can find from a data set. So let's do a training based on a set of behaviors, which I know. And then when it comes to the real driver that I'm serving, you actually can adapt your model so that learning what is the cognitive biases or cognitive rationality of the follower, and so that you actually can adjust your guidance policy online to serve the follower, serve the human driver much better. So, and the goal is to create I think this is a set of experimental setting. So where you actually can, hopefully there are obstacles in highway, and so that you can actually guide the driver from the very different initial conditions, so that can avoid the collision. Sometimes the driver itself actually can be very cautious and guide himself out of the collision, but sometimes the driver may be drunk, and you really actually need to help the driver to get out of the dangerous situation. And here is I think this is something that aligned with a lot of the things that we have said. For example, there's a KL regularization, and which actually is the one type of a quantum response, which try to capture drivers' decisions, which is with bound rationality. So in other words, you actually can use a quantum response or a KL regularized response instead of a linear programming type of solutions, and to actually quantify the outcome of the human's response to the leaders, to the assistant drivers signals. So, and also we need also create a meta learning process so that allow the vehicle to generate different strategies to assist different type of human drivers with the different characteristics. So, and I think possibly a good example would be the following. So I think this is some results here. So I think, I mean, I'm not going to go into details of it, but if you look at much carefully, you know, driver 1 and driver 4 are very different. Driver 1, apparently when it's obstacle here, the black dot is the obstacle. So it's actually is going to be, I mean, it's not going to change its lane, even though it's very close to when you see a black dot. And this one is the black dot is an obstacle here, but you can see that the system driving the machine is actually going to swerve much ahead of time, knowing that the human himself is actually going to do it, right? Because this is a drunken driver here. The driver 1 is going to be actually a more careful driving. So in other words, the action is not going to take in place by the machine and until, I mean, the driver is going to swerve by himself or leave the lane himself. So actually you can see that at a different drivers, and you actually have a different type of responses. So this is what interestingly can be done by not knowing what exactly the human model is, and just like the physics, but instead you actually can learn and adapt the policy online. So, and what we can show here is that this entire process is robust to drivers' bounded rationality and disturbances. In other words, there might be cases in which, well, you can give a driver a recommendation and the driver may not accept it, may not even use it. Now you actually can see that, well, this is actually knowing what is bounded rationality of what is the driver is, you actually can show that your recommendation is always going to be better choice for driver. So eventually going to guarantee more successful assistant driving. So this is my conclusion. The conclusion is very simple. I think, I said a lot of things today, and I think the starting point is that we start with the multi-agent systems, and then we talk about, okay, there is a need for teaming and coordination. But of course, apart from just a teaming and a coordination, there's other type of problems. For example, there's adversarial interactions, like it's thinking about a zero-sum game where you're encountering an opponent, somebody try to win, somebody try to somebody try to outsmart you, just like the lady in the lake problem. And as a part of the teaming and coordination process, we have a guided coordination, and then we have a Stackelberg dynamic games as a way to capture this guided coordination. And then we have introduced 3 type of examples. One is the assembly line example. The other one is the guided collision avoidance trajectory planning. The other one is assistant driving. But along the way, we recognize that, well, there is a need for learning-based solutions where we need to augment the Stackelberg games with the Koopman learning, deep learning, and meta learning, and also even a moving horizon type of computation in order to make the solution more adaptable and also adapt to unknowns. So knowing that, so the goal is really very simple in terms of this workshop. Well, why games? Why games and for dynamic? Why dynamic games and for multi-agent system? First is a framework. Second, it offers formalism and formalism for design and formalism for analysis and prediction. And at the same time, it also offers the robustness and flexibility through learning process. So this is the goal. And hopefully this workshop is going to fulfill this objective and helping people to understand the importance of dynamic games and its role in multi-agent systems. And that's it. Thank you.
Thank you so much. I wish we had your talk at the top of the day with them. I had good tutorials as part of it. So we have time for a quick question or two.
Yes.
Thank you for the great talk. My question is, so you are trying to like infer other agent dynamics, and then you choose Koopman operator to like linearize the basic dimension and linearize the operation.
Right.
So my question is, my question is, why don't you just use some general, for example, system identification, choose Koopman operator?
So why not use other?
Yeah, why
I think the good thing about Koopman is that suppose this is again is an offline process. Think about like say you have a lot of data offline, right? You actually can make use of the offline data to actually figure out what is the linearized model is. And based on linearized model, you actually can figure out what is the right way. I mean, what is the response that you would anticipate? So I think there are possibly other ways to do it as well. For example, if you do it just purely by neural networks, then you lose the dynamical system structure, right? You know, it's purely input-output. It's a black box. There is no physics that could be easily captured through that. But using Koopman allows you to capture it's in the midpoint between something that has a physical meaning, which is because it arises from a dynamical system, right? But also at the same time, also can assimilate data. So this is useful for that purpose. Now, this is useful also because of the application that we choose, right? Because it is we're dealing with the UAVs and UGVs. You have it's a mechanical system where we have a good description of the physics. Questions? I feel like I might have forgotten a lot of things to say, and because of the jet lag, but I would hope that there could be a lot of more questions that we could and there's a lot of hidden information I was not able to say in short time.